So today we are going to start lecture 55 in our optimization series, and this is a continuation of binary GA, and today I'm going to discuss the process of coding and decoding of design variables, which is very important for binary GA. And again, I'm Dr. Ranjan Ganguly. Now typically you have real design variables, and here we mean real numbers. And these are then expressed as binary strings in binary GA. And these strings are made up of bits, and bits essentially means zeros and ones. Now, the length of a string which you select is determined by the desired solution accuracy which you want. So let's look at some of these bits and strings. So again, let us say you want to constitute strings out of 2 bits. That is, you have 2 places and you are permitted to use either 0 or 1 for any of these 2 places. So you can only get 4 strings here, and they will be 0 0, 0 1, 1 0 and 1 1. So you can see this is 2 square, that is 4 strings. Now if you think of 3-bit strings, you can get 2 to the power of 3 such strings here, which you can see here starting from 0 0 0, which is the lowest, maximum is 1 1 1, and then there are all these steps in between where we have tried the different combinations which we can get with zeros and ones. So again, this is a process which you can continue. For 4-bit strings you will get 2 to the power of 4 such strings, and again you can go to the 5 bits, you'll get 2 to the power of 5, which is 32, and so on. Now we see that when we choose these bits, we get unique substrings. And here we are referring to those particular components as substrings, such as 0 0, 0 1, 1 0, or 1 1 in the 2-bit case. Now, frequently you may do combinatorial optimization problems where you have to select between several possible cases, or you have discrete design variables. So in this case, we can define each of those cases or each of those design variables by a substring, and the substring can then be used to solve the problem. You do not need your final solution in terms of continuous variables. For example, if we have a material selection problem and we have 4 material possibilities, we could say that the string 0 0 corresponds to steel, 0 1 corresponds to Al, 1 1 corresponds to graphite composite, and 1 0 to titanium. And then basically let the GA manipulate these strings and select the best material for the different parts of the structure. So in such problems, there is no need to move between the real and the binary domains. But most optimization problems involve real number design variables. So you not only need to know the coding part or the encoding part, but also the decoding part. So let us consider the case with 2 design variables, x1 and x2. Now in these cases, let us consider 4 bits to code each variable. So we start with 0 0 0 0 as the smallest value of the design variable, and then 1 1 1 1 is the highest value. So again, these are 4-bit values for each of the variables. So now if we think of a 2-variable problem, we have the variable x1 and x2, we have the lower and the upper bound on both these variables. Then the lower bound would be 0 0 0 0, that's one substring. Second substring would also be 0 0 0 0. In the case of the higher bound, you would have 1 1 1 1 and you would have 1 1 1 1. Now we can remove this comma here because we know that we have done a 4-bit coding, and we can write this as one string here, keeping in mind that each of these 4 bits corresponds to one substring, and this is x1 and this is x2, this is x1, this is x2. So this is how I can represent the design variable which existed in terms of real number in terms of these strings. So this is what we mean when we say we now have strings, we do not have numbers. Now two design variables led to this 8-bit string which we saw in the previous slide. Now let us generalize this concept and consider a generic string. So a generic string would have this form. So S equals all these values, and these are all bits, which means they are zeros or ones. And it starts from 0, 1, 2 all the way to m minus 1, where that's the number of bits you are considering totally here. So the decoded value of this string can be expressed by this formula. Decoded value of S is I is 0 to m minus 1, 2 to the power I Si. For example, if I have a string 0, 1, 1, 1, the decoded value of this can be obtained from this formula here. So I is 0 to 4 minus 1, m being 4, 2 to the power of I Si, and then expand this out in terms of S0, S1, S2, and S3. So now comparing with this and this here, you see that S0 is 1. That's the first part here. So this is 1, S1 is 1, S2 is 1, and S3 would be 0. So S3 would be 0 here. So this is the expansion which comes out. And then we take 2 to the power 0 is simply 1. So this is 1 plus 2 plus 4. And therefore we get 7 as the decoded value of this string 0, 1, 1, 1. So we have come here from this binary domain to this decoded value domain. But this is still not the actual value of the number. We will see that soon. So to think in terms of actual numbers, let us consider a design space where the lower bounds are 0 and the higher bounds are the number 10. And maybe this is some value such as meter or kg to give it some quantified form. Now the point in the design space represented by a substring can be found using this equation here. So let us say x1 is here. So I take xil, which is 0 here. I get xiu minus xil, which is 10 minus 0, by 2 to the power of 4 minus 1, since I have taken 4 bits, and then the decoded value of Si. So since this is 15, 10 by 15, I get 2 by 3. So x1 will be 2 by 3 of the decoded value of Si, and x2 will be also 2 by 3 of the decoded value of Si. Now these formulas can be used to obtain the actual design variable from the decoded value of the string. So let's say if we have the point 0, 0, 0, 0, the decoded value is 0. For 1, 1, 1, 1, decoded value is 15. And for a 4-bit string, there are 2 to the power of 4 is equal to 16 different substrings which are possible. So if we were to look at the two endpoints, x1 lower bound would be 2 by 3, decoded value of Si being 0, that would be 0. x1u would be 2 by 3, decoded value of Si, which would be 2 by 3 into 15, as we saw from the previous slide. So this becomes 10. So this is x2u. So this is how you get back the design variables from the strings for the lower and the higher bound. Now suppose you are in the middle somewhere and you have a generic string 0, 1, 1, 1, for which we saw decoded value was 7. In that case, xi would be 2 by 3 dv Si, and so that would be 2 by 3 into 7 equals 4.67. Now we are going to take a look at a table which is going to show the various decoded values for all the 16 possible strings and their mapped values into the design space. So you will see that these 16 possible strings provide a rough sampling of the design space, and the increments are 0.67. So you can look at this particular table very carefully. You see there are 16 points here. There will be all the points ranging from 1, 1, 1, 1 to 0, 0, 0, 0, which correspond to 0 and 15. We have our point 0, 1, 1, 1, which corresponds to 7. and then we have all the different points here. So it's actually taken this design space from 0 to 10 in the real number system for x1 and x2, and it has essentially sampled this space using 16 points. And all these points correspond to a particular decoded value. We see the decoded values range from 0 to 15, and again from this decoded value we can get the actual value of the string here. So again, this doesn't cover all the possible values within the particular design space or domain. It essentially samples it at some discrete points depending on the level of precision you have selected by the choice of the 4-bit string. Now, one thing that would come to the mind of many engineering type of people who love to get their solutions in terms of a large number of decimal places, that you could add more bits to each string and therefore you could get a higher level of sampling. For example, if you were to take a 5-bit string, that would result in 32 substrings, and that would be a denser sampling of the design space. Now, one interesting thing is that you can code different design variables with different substring lengths. Now, all the variables do not need to have the same level of sampling, and therefore this is something which can be tried out. Now, we clearly see that the number of bits used to represent design variable is going to be important for how correct your solution is in terms of the discretization, and also how much time it is going to take you to converge, because again, if you take a very high level of discretization, that may take more time. Now, generally, most users tend to use too many bits to represent the continuous design variable. So typically something like 4, 5, 6 should be sufficient for most problem. But many people are misguided by the machine precision of computers, and they end up taking a very large number of bits which may actually not be required for a problem. Now, if you have selected large number of bits, you are going to end up with long strings for the design variables. So essentially means there are going to be a plethora of zeros and ones in each string, and this is going to slow down the convergence of binary GA as well as increase the storage requirement, because remember, you have to carry the entire population size here, not just one string. So it's a better idea to study each design variable carefully using physical reasoning and to figure out the level of quantization that is needed. In some variables, you may be fine with a 2-bit quantization. In some variables, you may want a 5-bit or 8-bit quantization. That is up to the domain experts to figure out. Now, in many situations, there are design specifications, there are manufacturing limitations, etc., which contribute to the accuracy you require. Binary GA will explore the design space only to the desired level of correctness, which is predicted by this kind of quantization, and therefore you need to keep that in mind. Now, if you read the literature, sometimes strings are also called chromosomes, especially in the older literature, because when people came out of the biological theory of natural selection, they actually were looking at genes and chromosomes, and therefore the concept of strings was selected from there. So that's why the strings, being in terms of bits, are actually sometimes known as chromosomes. Now let us outline some of the key steps of the GA. Now we see that once we have encoded the design variables into bits and strings, you can perform the remaining steps of the GA. So when you are doing a binary GA now, you create a starting population. So let us call it P subscript I and IT, set generation as K is 0. You calculate the fitness of this entire population. That means for all the values at this population, at generation K, you create a mating pool, which is a subset of this total population MK. So these are the members of the population who have been selected for mating. Now this mating is typically performed using the crossing of genes between two of the points here. Then you also do some mutation, and mutation is a process by which you randomly change parts of the genetic material or parts of the bits of the different strings. And at the end of this process, a new population has been created. We will call it pk plus 1. And then you need to find out what is the fitness of this population, return to step 2 and continue this process till your process gets terminated. Now at each particular cycle which you go through here from k is 0 to k plus 1, you essentially go through something called a generation. So this word comes from the typical concept of a generation being a group of people who are born at a particular time, and the next generation is their children and their progeny forms the next generation and so on. Now typically GA are terminated after a maximum number of generations is reached. And what you do at this point is that you take the best fitness value fx star during all the previous points and then extract x star which corresponds to this fx star value. So this is somewhat different from gradient based methods where we are actually working with x star. So here in GA you are working with fx star and you keep a track of the best fitness value which has been obtained throughout the generations for all the points and the population, and then at the end of the convergence of the GA you pick this x star value. And like I mentioned before, sometimes GA is run several times so that you take the best possible value by running the GA 5 or 6 times or maybe 10 times. So in many papers you will see that GA is run 10 times, generation is something like 50. So these are some typical values and the best value is taken. So one more possibility is that if you are not getting any better as the generations progress for a long time, then also you can terminate the process, which essentially means that you keep comparing the best value at different k values. And again, if x star is not changing, you can terminate the process. So the process of GA is not very mathematically focused in terms of taking the gradient vector and checking it is 0 or not, though there is nothing stopping you from doing that for these points. But typically when you are dealing with these kind of stochastic methods or methods which do not use gradients, you do not actually want to calculate gradients because that becomes one more cumbersome thing to do and you are in some effect defeating the whole purpose of using GA. So what is done is typically you use the function values to make any decisions about this process. And because in the next lectures we are going to see the starting population is largely generated randomly, you can run the GA several times and then take the best value, and this is going to give you a better result than spending your time in calculating gradients and so on. So again, this was an introduction to the binary GA. Next video I will discuss about how to create the starting population, and then we are going to look at how to perform those different parts which are involved in the reproduction process and the selection of the best particular candidate. I'll see you in my next video.